Hello. Okay, so I would like to illustrate an example in in type theory in general. So first of all, I want to say I took this example from a book called Type Theory and Formal Proof, an introduction by Rob Nederpelt and Herman Geubers. The book talks about a certain style of type theory. Um, and it talks about a couple basic type theories, basically, that are then put together to build a type theory called the calculus of constructions, um, which is the underlying type theory behind the Koch proof assistant. So that's the reason why I think you should be interested in this. So what are the languages? So there are basically in the beginning of the book, the languages are more basic and they build up in complexity. Uh, and then at the end, they're all combined to build this complicated type theory called the calculus of constructions. Um, and we start with simple type theory, which is the most basic type theory. Uh, and then it is expanded in three directions. Uh, and these are then combined to build the calculus of construction. So you can look at these type theories as forming a cube, in which every corner of the cube is a type theory, like a little language that you can do proofs in, um, like do logical deduction. Yeah. So this bottom left corner here. Oh, I thought I could draw on there. Wait, let's see. Yeah, let's try this. So this lambda arrow thing, this is the simple type theory, and it will later be expanded in every direction. So this is lambda p, for example, is a type theory that expands simple type theory in a certain way, and so is this one, and so is this one. But I won't get into those in this video because we're starting off basic. So what exactly is such a theory? It's a simple language in which every sentence has the following structure. Every sentence can be divided into three parts, and every part has a certain sub language, I guess you could call it, or it has a little language on its own. Then you stick the three parts together and you get a sentence in the type theory in question. So the terms correspond to sentences in lambda calculus. Like you might know this if you know some programming. So, for example, you write the identity function like this. Oh, so this amounts to saying, I'm defining an anonymous function that takes one parameter and it just gives it back. So this is the identity function. Like if you had a class on calculus, you might know it as f of x is x. Whoa, my tablet is being weird. Right. It's this function. If you're looking at real numbers, but we're not doing that. Then the type corresponds to something in logic. Oh my God, it's really annoying that my tablet keeps messing up. So the type corresponds to something in logic. So in the simple type theory, it just corresponds to variables with implication. Oh, yeah, and the variables are written as Greek letters. So alpha implies beta implies gamma, something like that. So this is a type, which you probably also recognize from programming, right? This is a if you've seen some Haskell, this is just a type of a curried function that takes two parameters and spits a parameter back out. Okay. So that's what the types are. And then the context is a list of variables where every variable has a type. Wait, so let me grab my book real quick. Yeah, so an example would be y goes from alpha to beta. Whoa. So this amounts to, so a context amounts to a scope when you're thinking about programming. So if you're at some judgment where this is in the context, then it is as if there is a variable defined at that point. So you're in a scope where a variable y is defined as having this type, right? Okay, so that is what a judge. So sentences of this with these three parts are called judgments, and then you can ask. But in the type theory, you can ask questions about these judgments. So in every one of these eight languages, or in every one of these eight type theories, you can ask three types of questions. The first type is well-typedness, which is you're given a term, such as lambda xx, right? And you're given and you need to figure out if it is possible to construct a judgment where that has the term in the middle and it has some context and some type. So this would be if you're. I keep the way I make sense of these things is by relating it to programming, right? Because that's where my background is in mainly. So I think you could think about this question as if like you're given some. Oh, so you could think of this question as you're given some program without types, like a Python program. Oops. And then you give it to the type checker or to the compiler, and the compiler tells you whether or not it makes sense. So in Python is maybe a bad example because Python doesn't do very much checking, but it would be like as if you let's say you wrote a Python program in which you add a number and a string. Then Python is going to tell you, hey, this doesn't make sense because you're adding two things of different types. So that would be an example where you figured out that it's not typable. But if you give the Python compiler a program that does make sense, it's as if the compiler solved one of these problems. Right? You gave it a term, and it came up with some reasoning as to why it's probably right. But in Python, it's obviously way less formal. I don't know how the behind the scenes works of Python. Okay. Then the next question you can ask yourself in one of these theories is type checking, which means you're given a judgment, and you're posed to figure out whether or not the judgment makes sense in the language. Yeah. And then the last type of question, which is relevant to mathematics, is you're given some type with a context, and you're supposed to find a term that inhabits the type. And you can think of this because, okay, there's a thing, I should have maybe explained this up front, but there's a theorem or an idea. I don't think it's called a theorem. It's more like a thesis, um, called the Curry-Howard correspondence, which says that tr- in somehow, but it's not a super formal theorem. Like I said, somehow programs and terms are related. Programs and proofs are related to one another. And in type theory, this is almost crystal clear because terms correspond to uh, computable functions like lambda terms, and types correspond to statements in logic, right? So if you're given a type and you're figuring out a term, it is as if you're proving something. You're building a proof object. Okay, and so in mathematics, you're it usually makes. I mean, I think it only really makes sense if you end up. So your proof ends with something where the context is empty. So I'll explain this. I mean, I hope this will become clear by the time I finished doing my practical example. But if you use a variable in these type theories, if you, yeah, I'll just show it by example, and then I think it'll make sense. Okay, so now for the actual practicalities, this is where we get into the meat of everything, right? So the example I want to show, if you have this book, it's on page 45. That's the example I want to illustrate. So, but it is phrased as a, okay, I think they just show the finished thing, right? But I'm gonna try and show you how you might derive the thing that's shown there. So the thing that's shown is a complete proof, where on the last step they derive a certain judgment. Okay, but I'm gonna look at only the type right now and hide the complete judgment for you right now, and then hopefully we will derive it. Right? So the type of the final judgment. Oh, the type of the final judgment is the following: lambda a, b, alpha beta implies, oh man, implies alpha, implies beta. Oh my god. Okay, I should buy a new tablet, I guess. Right. So this is like a question in logic, but we pretend like we don't know that right now. So there's no meaning attached to this sentence. But you could look at it as a statement in propositional logic, right? Now, if we look at it as a type from a programming language, this amounts to the question of you. So to write it in some Haskell, let's say I need to refresh my Haskell syntax a little bit maybe, but I think you could write it in Haskell like this, right? F dot 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 alpha beta, or yeah, you can't do Greek letters in alpha, but whatever. So we're trying to define a function that takes that takes two arguments. It's a curried function. It takes two arguments. The first argument is a function in its own right from a to b. So f is a higher order function. It takes a function that when you plug an a into it, it gives you a b. It takes an a and it gives you back a b. So it's as if we've plugged the second argument into the first and received the b, right? So intuitively, it is very clear that this thing should be, it should be fairly easy to find a term for this thing, right? So I'll show you how it works right now. So this is the question statement. And I'm going to do the proof in flag style. So in a flag style proof, you can do a couple things. You can introduce variables. This is like how you do it in programming languages. And then when you introduce a variable, you plug something into the scope, into the context. Sorry. And then once you're inside a certain scope, like inside a environment in which there is stuff defined in your context, you can do a couple things. You can plug the variables into one another. Like if you have a variable of type, okay, I'll just show you. So first of all, we're going to introduce a variable called y of the following type. Okay, you write it like this. So this is a flag, right? Then we introduce another variable called x, which is of type alpha. Okay. So this might be a little bit confusing right now, like what we're doing exactly, because I was talking about these judgments, and all of a sudden I'm writing these flag thingies, but it'll become clear as I work through the example, I think. Then, let me grab the example just to make sure that I'm not doing something wrong right now, because I don't want to remake this video. Yeah. So now we've expanded the context with two variables. And now we're going to write our first judgment completely. So now we're just going to say, okay, since this thing is in the context, we can use it. And this surmounts to using the var rule. So every one of the 8 type theories of the that is very unreadable because my tablet keeps being weird. Oh my god. Okay, so every one of the 8 languages of the cube has a set of rules, deduction rules, which define how to go from one judgment to another. How can you, in your reasoning, conclude something from something else, right? And var, so a proof is like, you can look at it as a tree structure, right? You assume some things. Oh my, this is so annoying. You assume some things. So the assumptions are like the leaves of the tree. Then you combine some of your assumptions and you reach some conclusion. Okay. Assuming stuff in simple type theory surmounts to taking something from the context and declaring that it exists, sort of. And that's the var rule. Okay. So using the var rule, I'm going to derive 2 judgments. Okay. Yeah, and I'll explain the flag format right now. So this judgment Wait, I don't know. I'll pick a different color real quick. Oops. Green. So the first judgment we're writing down here uses these things in our flag style proof. Okay. So these two things are in our context. This is our term, and this is our type. Okay, so those are the three parts of our judgment. And then for the second term, the exact same thing. So these are, every line here within a certain scope corresponds to a judgment. So on the second line, our term is X, our context is the same. It's these two variables, and then our type is alpha. Okay, then to keep going on the proof, I should have made a bigger page. Wait, how am I gonna do this? Maybe I can just like shift everything. Sorry. Okay. Yeah. Maybe I'll just forget about the title right now. Okay, let's keep going. Then, I removed the X. Oh man. Let's try making. Okay. Then, so that's what we had. We used the var rule. Oof, that's annoying. We used the var rule again. Now, this is where the magic is going to start happening. Now we plug X into Y. So Y is a function, right? It's something where the type has an arrow in it, and X is a variable. Now we plug X into Y. And this has, so we have something that goes from alpha to beta. We plug an alpha into it, so we end up with a beta. And when you plug a variable into a function, you're using a rule called APPLE, which stands for apply. Wow. Man. Ooh. I guess for next video, I'll buy a new tablet. Apple. Okay. Oh yeah. Well, and to be completely clear, you can like give line numbers, and you can say, okay, I applied Apple to 1 and 2, right? Then we keep going. Okay. Wait, let's make everything just smaller so it fits on the screen. Okay. Then we've used Apple. Then judgment 4. Let's see here. Now we're going to start using the third rule of the system, which is the rule abst. And that's where lambda abstractions are going to come into play. So now we do abst on the last line to derive the following term. Yeah. Lambda x. Oh wait, no. So okay, yeah. We're leaving the x scope right now. which is why we're yeah, I'll just write it down and it'll make sense hopefully. Oh. Okay. Okay, we did abst on 3. So when you're doing the abst rule, so there's an ordering to the context. So you need to make sure to, in your proofs at least, meaning wise, it doesn't, if you write down a judgment and you flip to arguments, 2 of the variables in your context, meaning wise, for one judgment, it doesn't matter. But in a proof, if you're writing it in this flag style, it does matter because it is implied if you do the abst, if you apply the abst rule, the last thing that you introduced, like the last nested scope, you leave, which you then tack onto your term as a in the form of a. Oh, I should have closed this parentheses here. Oh, they don't even use parentheses in the book. Okay, whatever. So ignore this here. So in this abst rule, when you're doing it in this style that the book uses, instead of drawing a little tree, if you use the abst rule, you leave the highest scope level. Yeah. So, and then you tack onto you should denote next to your abst rule what line you're applying it to, what line you're abstracting away from, sort of. I don't know if that makes sense, but so as you can see here, this thing is the inside our lambda term, okay? And our scope has shrunk. The X has disappeared from the context. So the current judgment uses this stuff here. Okay? So the context consists of one variable, y. Our term is this here. And this is our type. So those are the 3 parts of the judgments again. And then we're almost there. Let's see if I erase the... okay, I erased the assignment statement. But we're going to do another abst rule application. Okay, it's confusing. We're not doing Apple, but we're using the rule abst again on the last line. So abst on 4. So we're removing the y from the context. And then we come up with a judgment. Okay, maybe I'll write it in green just to make it clear that I'll write it so that yeah, then we plug x into y. And then, oh yeah, and then we have something that takes an alpha. Oh. Okay, maybe I'll try writing it with my mouse because this tablet is useless. Alpha, beta. Okay, sorry, I'm doing some line wrapping. Then we take an alpha, and we give back a beta. Okay, so this is our original problem statement, right? And now we have a judgment where the context is empty. Let's see here. This is the term. Oh wait, no. All of it leading up to the box here. This is the term. And this is the type. So this was this thing here, alpha, beta, up, up, alpha, beta. This was the original problem statement, right? And we've managed to construct a judgment where the context is NP. And we have a term that inhabits this type. So you can now look at this thing we've derived in two ways. You could write this thing in your favorite programming language that supports Lambda terms. Then you have a little program. You can also look at it as a summary of this tree here, or this flag style proof, which translates to a tree. So therefore, you can look at this term in two ways. That's a Curry-Howard correspondence. It's a program and a proof at the same time. So that's all. I hope this made some sense, and that's how you prove something in simple type theory.